Okay, so let me remind you what we did yesterday, or what was the upshot of the whole thing. So yesterday we saw that we talked about the Higgs mechanism in the standard model. And we said two things about it. First of all, it's not fully tested yet. And the other thing is that it leaves theory questions unanswered, completely unanswered. In a way, it's sort of an ad hoc description of what we need for electroweak symmetry breaking. So all of this suggests some new physics. And this new physics can be possibly not far above the reach of the LHC. And so one way that we can parameterize that is via effective field theories. And we saw some examples of EFTs. We saw that in different contexts of the standard model, we encounter effective field theories. So this is a very natural thing to think about. And so essentially what we want to do is we want to write some Lagrangian, which is the standard model Lagrangian, augmented by some EFT Lagrangian. And these new effects here can serve two purposes. First of all, as we said, we can use them to search for new physics. But another way to think about them is just as a way to test the standard model. So these are very, very similar, but slightly different in spirit. So as we said yesterday, one way to test the standard model is to calculate something very, very precisely and compare it to experiment. And another way to do that is to come up with an alternative and try to look for the alternative. Okay. And what this effective Lagrangian is going to do is it's going to give rise to effects that grow with the energy. So they're suppressed by the cutoff, the EFT cutoff lambda. And one thing that we said yesterday, and I want to repeat, is that if we take the standard model without the standard model Higgs, or alternatively, if we just take the standard model Higgs and fiddle with it, like change its couplings, then this theory on its own can only be an effective theory because it has a cutoff which is of order the electroweak scale. So this is something that's been known since the 70s. People doing a lot of very, very hard work realized back then that if you have the standard model particle content or field content, then the only way for this theory to have perturbative unitarity is if you really have the full standard model gauge symmetry with the Higgs, with the Higgs doublet, as dictated by this symmetry. So if you just have a single physical Higgs, so that's the standard model particle content at low energies, the only way to have perturbative unitarity is if you have gauge symmetry. And so this is something that if we have, this is something that we already said yesterday, but I want to highlight this because we'll come back to this. And if we have enough time, we'll even see how immediately that comes about using amplitudes. Is there a question? Okay. Okay, by the way, one thing I want to emphasize, because someone asked me, when we talk about the problems with theory questions with the standard model Higgs mechanism, I emphasize naturalness. And someone asked me about that versus hierarchy. So the hierarchy problem sometimes is, if you just call this the hierarchy problem, then it seems that the only problem you have is the fact that the electroweak scale is much, much smaller than whatever fundamental scale you think you have, for example, the Planck scale. But that's not a worry in itself, because as we said yesterday, we have lambda QCD. We never worry about that. It's naturally suppressed compared to the Planck scale. We have the electron mass, which is even smaller than the electroweak scale. We never worry about that because we have chiral symmetry, which protects the electron mass. So it only depends on the cutoff logarithmically. So this is a very mild dependence on the cutoff. And the Higgs mass is different because it depends quadratically on the cutoff. So that's why I want to call it the naturalness problem and not the hierarchy problem. Okay. Good. So now the thing that we want to do is we want to find, this is getting progressively harder, I guess. So now what we want to do is we want to find the most general EFT extensions of the standard model. And what I mean by that is that it's only going to have the standard model particles at low energies. And we want to do that using the amplitude bootstrap. So instead of working with Lagrangians, I want to do this using amplitudes. And the reason is that this is a much simpler way to derive the EFT than to use Lagrangians. And you'll see that it's very, very simple. Okay. So what are the things that we're actually relying on? So we want to write the most general amplitudes. If we write the most general amplitudes, so we have an amplitude in terms of the standard model fields, we want to write down the most general amplitude. So the things that we need to take into account are the properties of amplitudes. First of all, there are things that are going to come from Lorentz symmetry, and in particular, the little group. But also there are, and then there are, of course, various global symmetries that we'll need to talk about. And then there are the essential properties that we're going to use, which is unitarity that we already saw, and locality. And as I said, I'm going to talk about amplitudes of particles with spins, the standard model spins, which I'm interested in for the standard model. Okay. So let's state very simply what are going to be the ingredients here. So unitarity is, of course, coming from the statement that the S matrix is unitary. And then since, roughly speaking, I can write the amplitude is this part of the S matrix, the imaginary part of A is proportional to A squared. And then locality tells us that the amplitude is an analytic function of the momenta, or more precisely, the Lorentz invariant, or the Mandelstam invariant. And it's an analytic function of the Sijs in almost the entire complex plane, except at some except at some isolated points where it has simple poles and some branch cuts. And both of these are coming, all of these are coming from some particles going on shell. And the crucial thing is that we know what the amplitude does at those points. We know what these discontinuities are from unitarity. And so, we know that at the poles, the amplitude basically factorizes onto lower point amplitudes. So this is just schematically for a 4-point amplitude, and for the cuts, these cuts are coming from several number of particles going on shell. And in each case, the discontinuities are determined, or the discontinuities of the amplitude with n external legs, they're determined by the amplitudes with a smaller number of legs. So for the most part here, I'll be interested in tree-level stuff. So I'll just be interested in these poles. And here we know that the residues are given by what I can call A left times AR. That is this amplitude times this amplitude. So altogether, near this pole, the amplitude we have a pole of the form 1 over p squared minus m squared times this AL times AR. And knowing these singularity structure is the thing that allows us to recursively build higher and higher point amplitudes. So that's the fundamental thing that we're going to rely on. Okay, now we already said yesterday that we saw another, so this is one thing that unitarity in combination with analyticity tells us. We already saw yesterday another thing that unitarity tells us. Which is the fact that any bed energy behavior has to be accompanied by the cutoff, has to be suppressed by the cutoff of the EFT. So that's sort of the 0th order thing that you need to know about the EFT Lagrangian, that higher dimension terms are going to be suppressed by powers of this lambda. And so essentially, this is the thing that we're going to construct. Of course, if we look at unitarity more closely, so the statement essentially this statement here, if we look at it in more detail or more quantitatively, there's more information that you can extract. For example, when you write this EFT Lagrangian, okay, we know that En terms have to come with the lambda to the n, but you can ask the question, are all the Wilson coefficients, so we said this involves lots of Wilson coefficients, so you can ask whether all of them are allowed. And the answer to that is, in general, not all of them are allowed. When you really plug in your amplitude into this simple relation and see what it implies. So these sorts of constraints go under the name of positivity constraints. In some cases, they constrain the coefficients to be positive, or some combination of coefficients to be positive. So if we have time, we'll talk a little bit about that. Another thing that it tells you is, as we said here, some of these discontinuities have to do with the cuts of loop amplitudes. And so another thing that you're interested in the context of EFTs is you're interested in the running. And the running, of course, is coming from the loops. And loops can be determined by their cuts. So again, we can get lots of results about the running coming from the cuts that involve lower point amplitudes. And so this is another place where the amplitudes really simplify things. So this is sort of the overview, but the thing that we'll start from is the very basic thing, which is just determining this EFT Lagrangian to lowest order. Okay, questions before we go on? Okay, oh, and by the way, one thing that's related to, so we had a really nice talk by Sebastian earlier where we talked about the soft limits of photons. So here we're also interested in the Higgs mechanism. And so as someone asked before, another limit that's interesting is to think about the limit that a scalar is soft. So what happens when you take a scalar to be soft? That obviously is related to the Higgs mechanism. There are two scalars that you can think about. One is sort of like the Higgs, another one is a Goldstone. And the soft limits of both of these guys are interesting, and hopefully we'll get to talk about them. And in particular, when you take some scalar to be soft, you're sort of implicitly assuming that it's massless, so you can take its momentum to 0. And so it's some sort of modulus. And so what you're doing when you're taking some scalar line to be soft is you're essentially probing the moduli space in which your amplitude lives. So this is something that we'll get to hopefully tomorrow. Okay, very good. So for now, we just want to bootstrap amplitudes. And the place where we stopped yesterday was the very first thing that we need to do. We need to understand how to write amplitudes. And so I'm going to start by talking about how to write amplitudes. And the essential ingredient here is Lorentz. And as I said, we're going to use two-component spinners to do that. So you guys said that you're all experts in meshless spinners, so I'm taking your word on this. And if you're not, then you can talk to me and I'll point you to the right references. But let's quickly review what happens for meshless amplitudes. So here's some leg with momentum P. where p squared equals 0. And so we know what to do here. If this guy is a fermion, it comes with a fermion polarization, which is either this type or this type of spinor. And if it's a spin one guy, then it comes with a polarization vector, which we can write as follows. For positive helicity, we can write it like this. And if it's, let me write it here, and if it's negative helicity, then we can write it like this. And what this R is, it's some arbitrary spinor that we can think of as a reference spinor. And of course, we have this freedom because we can change this R to some R prime. And the only thing that's going to happen is that this epsilon is going to shift to epsilon plus some number plus p. So the word identity tells us that this doesn't make any difference, and so we don't really care. Okay. The other thing that we should know here is that we can write this light-like momentum in terms of spinors. So I can write P is an angle times square spinor. And that's all very nice because now at the end of the day, the amplitude is given completely in terms of these spinors and spinor contractions. So A just involves things like Pi Pj or Pi Pj, and we're going to abbreviate this like this. And just to remind you that these guys are actually complex conjugate, and Sij is equal to Ij Ji. Okay, so hopefully you're all familiar with that. And if you're not, then it's easy to catch up on. Okay, one more thing that we need to know is what's called as Schouten identities, and I never know if I'm pronouncing it correctly or not. But what these identities are just reflecting the fact that these guys, these I's are two-dimensional spinors. So because they're two-dimensional, there's only two independent ones. And so I can write any spinor K in terms of two independent spinors I and J. And now if you start taking dot products, like take the IK here and then take the product with J, and then take the product with some spinor L. This I'm not going to do here, but it's a simple exercise. If you don't know this, you'll find that IJKL plus IKLJ plus ILJK equals 0. And similarly for the square brackets. Okay. So this is for massless particles. But in nature, we have lots of massive particles. And here we're primarily interested in electroweak symmetry breaking. So masses are the most important thing. So we want to know about massive amplitudes too. Okay, so now let's assume we have some non-zero mass. So now our p squared is equal to m squared. But now I can use what we said before about massless momenta. So the point is that I can write any massive momentum as some k plus q, where each one of them separately is light-like. So these guys have to satisfy that 2k dot q equals m squared. And now we're in business because these guys, the k, I can write in terms of these spinors, and similarly, I can write q in terms of spinors, and now we know how to do things. Now, notice that when I'm splitting p like this, all I need to choose is I need to choose one direction. Let's say k hat. Once I chose k hat, I'm done because this thing fixes q hat and fixes all the and fixes the magnitudes of these guys. So this is exactly what we expect for a massive particle. We said yesterday that a massive particle is characterized by two directions, the direction of the momentum and the direction of the spin axis. So that's exactly what's happening here. I have the direction of the momentum, and this guy can be the direction along which we're quantizing the spin. So this makes a lot of sense. Okay, but now we can introduce more terminology and more notation to make this thing nicer. So we want to make this little group covariant. We don't want to fix it to be some fixed k and q. So we can let's call this guy pi equals 1, and this guy q, I want to call pi equals 2. So now my big i's are going to take the values 1 and 2. And these are going to be the little group indices, as we'll see very soon. So now, using the results that we had before for the massless spinors, we can write P is epsilon ij. Well, let me just write the sum right away. So I can write it as pi where I'm summing over I equals 1 and 2. Okay, any questions? And now let's turn to polarizations. So again, let's start with fermions. So for fermions, we know the familiar spinors, which are the solutions to the Dirac equation. So now we can write them in terms of pi and pi. And remember that I takes the value 1 and 2. So that's what we expect, because we should have two solutions to the Dirac equations corresponding to the two spin states. And you can check that the Dirac equation is satisfied for these guys. And by the way, all my conventions are from this paper. Okay. And then we can turn to spin 1 particles. So for spin 1 massive particles, we have 3 polarizations. Let me write first something that's familiar. So I can write this as P1 sigma mu P1 over 2m. And I can write epsilon minus as P2 sigma mu P2 and I can write the zero polarization as 1 over 2m times P2 sigma mu P1 plus 1 and 2 exchanged. So I mean, this isn't, I said this is familiar. This is a familiar way of writing the spinner, the polarizations. Basically, it's using it's using 2 spinners here, this square one and angle one. And I haven't showed this, but it's very easy to check that this is indeed what you have. And we can abbreviate this in the following way. So we can write epsilon mu ij is P, I'll explain the notations in a second. And here, what I mean is that I'm hiding the, okay, I shouldn't really write the ij's here. So what I mean is that the ij indices are implicit. So the I and j indices are always symmetrized over. Here they can take the values 1, 1, 2, 2, and 1, 2, plus 2, 1. And this underline here means that I'm not showing them. So they're simply hidden here. There's an I here and a j here, and they're symmetrized. And so I was sort of very brief here. It's easy to check the algebra here. I just don't want to spend a lot of time on it. But it actually makes a lot of sense that what we're doing here is we're using the fundamental representations of the Lorentz group, 2-component spinners, in order to build all the different representations that we need. And we're taking symmetric combinations of these guys, because anytime you were taking an anti-symmetry combination, you get a singlet, right? So that we're just adding spin 1/2 objects. Okay, any questions? And one more thing. So my underlines here, this is where, this is, instead of using the bold notation, so this was all introduced by Nima, Huang, and Huang, and they use bold notation to denote this implicit symmetrization, but it's impossible on the board, so I'm using underlines instead of that. Okay, questions? Yeah. Symmetrization of ing. Yeah. So that anytime this underline means that I'm symmetrizing I and j, and they're implicit. They're not shown. Okay. Yes.
I'm not good at symmetrization origin, so the choice of k and q is quite arbitrary. You can choose any k and q that satisfies that true.
Exactly. That's exactly the point. So the point is that you have, let's say this is my p, or this is the 3 momentum. The point is that I can choose k anywhere. So there is this this whole rotation that I can do here. And we're going to come back to this in a second. Okay, good. So now we can write down all the amplitudes that we need for the standard model particles using a uniform notation. So that's one advantage of doing things this way. But then another one is the fact that we can see the little group very clearly. And so let's talk first of all about m equals 0. So for m equals 0, we said that we can write the momentum as p. And of course, I'm free to rotate each one of them by this guy by a phase and this guy by the opposite phase, because they're complex conjugates of each other. And this is exactly, so there is a U1 here. There is a U1 rotation of the spinors that leaves the momentum invariant. And that's exactly the little group. That's what you expect for the little group, because this is a massless particle. So its momentum, I can write its momentum as E0, 0, E. And then the Lorentz transformations that will leave the momentum the same are the ones that rotate these two guys. So that's essentially an SO2, and that's a U1. Okay, so that's one thing. The other thing is we can do the same thing for a non-zero M. So here my momentum is Pi Pi. And now I can, and these guys, remember, are two-component objects. So I can rotate them by some SU2 matrix. And here I can stick the inverse matrix, because again, they're complex conjugates of each other. So this is W dagger, which is W minus 1. So again, what we get is an SU2 that leaves the momentum untouched. And that's what we expect, because for a massive particle, I can go to the rest frame. And this is the momentum in the rest frame. And now I can rotate this guy, and I won't touch the momentum. So that's an SO3, which is an SU2. Okay. Excuse me? Why SU2 and not U2? That's okay. Why do I want the determinant here to be 1? Well, I do have, yeah, you're right. I mean, a priori, it would seem like it is a U2, but there is some, it sort of has to do with what I want to do with my mass, because remember that my P squared equals M squared. So that means that P, like if I take P1, P2, this thing is equal to M. And so this extra U1 has to do with whether I want to rotate M by a phase or not. Once I give up on that freedom, that restricts me to the SU2. Okay, so I'm actually going to choose, so Pi Pj is going to be, let me see if I have that. Okay, roughly speaking, I don't want to, I'm going to get the signs wrong if I try to do it, if I just try to do it off the top of my head, but roughly speaking, as I said, this is this, and then there's also P1, P2, and I'm going to take them both to be M. Well, here, it's probably minus. Okay, good. So the thing that's going to be, so this is something that we're going to use very, very heavily, because the amplitude is covariant under Lorentz. So of course, if it's a scalar amplitude, it's Lorentz invariant. If it involves particles with non-zero spin, it's covariant, and so it needs to be covariant with respect to the little group 2. And so essentially, the little group covariance of A determines how it, what are these spinors that it's carrying. So for spin 1/2 guy with momentum P, I have to have some P or P. And again, these are underlined because these are massive now. And for spin 1, I need to have, well, actually, okay, so this, I can do this for spin for either m equals 0 or m or non-zero m. So this holds for both. For massless particles, these two are allowed, and this two, and this one is not. But for m, for a massive vector, I'm also allowed to have this combination. Okay. And so that's going to imply various selection rules on the allowed amplitude. Okay, very good. So now we can start playing with this and bootstrap the amplitudes. Okay. Okay, so let's start with the simplest thing. So I want to write the most general amplitudes involving the standard model fields, or standard model particles, to be precise. So let's take the simplest amplitude. And actually, I want to start from massless amplitudes. So I want to take the simplest amplitudes. And so I want to look at 3-point amplitudes and start to classify them. So these are the simplest. But what's the problem with them? Exactly. They don't exist. Okay, there's no such thing. I mean, we all know that a photon cannot go to that one gluon cannot go into 2 gluons, okay? There's no such thing because I can't have P1 plus P2. I can't have momentum conservation together with, I cannot satisfy energy conservation and momentum conservation at the same time. Actually, what's the only asterisk to this? What's the only case where we can think about this? Sorry. An external field, right? But I'm not talking, everything's dynamical for us. So think, before lunch, think about what happened before lunch. In the limit that we have soft particles, okay, or collinear particles, that's the only case where we can think about these 3 points. And in that limit, that's when they're physical. So I can satisfy momentum conservation if one of these legs is soft or one of them is collinear. Okay, but it's very useful to think about 3-point amplitudes as sort of the basic building blocks of everything that you need. So in order to circumvent this thing, what's the thing that you usually do? You talk about 3-point amplitudes all the time. And what allows you to do that? Complex momenta, exactly. So if I take these momenta to be complex, I can talk about these amplitudes. And I'm not too perturbed by that because we work in the complex plane all the time, right? We talk about the analyticity of the S matrix and all that. We sort of live in the complex S plane. So usually we think about just leaving the real axis a little bit, but now let's go all the way into the complex plane. So that's what we do. But you should keep in mind that these things are completely unphysical. And when we talk about massive particles, this is going to change because a massive particle can decay to two massless particles. And this is the only case where these 3-point amplitudes become physical. Okay. So, good. So we still want to talk about these 3-point amplitudes. And so let me remind you what happens for these amplitudes. So I have momentum conservation. Just like in Sebastian's talk, my momenta are always incoming. So I know that P3 squared is 0, but that's equal to P1 plus P2 squared. And this thing I can write as 1, 2 times 2, 1. So that tells me that either this guy is 0 or this guy is 0. So let's imagine that this guy is 0. So 1, 2 is non-zero. And now I can look, for example, at 1, 2 times 1, 3. But this I can write as minus 2, 1, 3. And now I can use momentum conservation to write 1 is minus 2, minus 3. So this thing is also 0. So since I assume that 1, 2 is non-zero, this says that 1, 3 is 0. So when you're talking about 3 points, you are talking about a very special kinematics in the complex plane. You either have that all these guys are 0, and then the only non-zero objects are the angles. So this is sometimes called angle kinematics, or all the ij's are 0. Yes.
In one of those brackets, what do you mean then? I know those two Phoenix brackets, but what do you mean in the Phoenix?
So what I mean is that, so we're talking about the 3-point amplitude. So I have 3 external lines, 1, 2, and 3, with momenta P1, P2, and 3. And I'm writing them in terms of these spinors for P1, P2, and P3, right? And so maybe I didn't understand the question.
Yeah, I didn't know you. But always was brackets always that one spinner onto another, right?
Yeah.
Now you have 3 spinners or 3 pins in one bracket. So what do we contract or what?
Oh, everything is complex. Oh, I'm always contracting with an epsilon tensor. So anytime I have, so this ij is really.
Yeah, okay. Yeah. What do you mean by ijk? So you're like,
Oh, okay. Yeah. So what I mean by ijk, by this guy.
yes.
Yeah, okay. Right. So this, remember that P is P, I can write P like this if it's P alpha alpha dot, or the other way around if it's alpha dot alpha. So all that's happening here is that I'm using, I'm saying, for example, this 213, what it is, it's 2, P1, 3. Okay. Yeah, yeah. And then I'm sticking in this P1. So yes, it's confusing notation in the beginning. So is this clear?
Yes.
Any more questions? Okay. Okay, so this is really good because now if all the 3 points are constrained to be of either angle type or square type, then that means that because we have these selection rules for them coming from the little group, we can fix them completely. And that's really what we can do. So let's do this for an example, which is the first example I want to do. Okay, so let's ask what's the 3-point amplitude of 3 spin 1 particles. And so I have particles with P1 that I'm denoting by 1, and some helicity H1, and then 2, H2, and 3, H3. And first of all, let's just look at the Lorentz structure. So we said before that since these guys are spin 1, that means that if, for example, this H1 is +1, then I should have a factor of 1, 1. I should have 2 spinners, 1. And similarly for the other guys. So what this amplitude is going to be is it's going to be some constant times 1 to the power n1 2, 2 3 to the power n2 3, 1 3 to the power n1 3. And and now we can look at what the little group tells us. So the little group tells us that n12 plus n13 has to be equal to 2h1. That is, if 1 has plus helicity, I need to have it appear twice as a square bracket. And similarly for the other guys, so S13 plus S23 equals 2H3, and N23 plus N12 equals 2H2. So you can sum these up and find that N12 plus N13 plus N23 is equal to the sum of the helicities, and that can be either plus or minus 3 or plus or minus 1. Okay. Now, one other thing we know is we know that the dimension of an n-point amplitude is 4 minus n. And if you don't remember why that's the case, just look at your favorite QFT book and look at how you calculate cross sections and check that that's indeed the case. And so for this 3-point amplitude, its dimension is 1. So now let's look at different cases. First of all, let's ask the question, I have this coupling C that I wrote down here. So let's imagine that C, the dimension of C equals 0. So then I have that this sum has to be equal to 1. And that means that the sum of the helicities has to be equal to 1. Okay, and then we find that the amplitude is of the form C0. I'm denoting the dimension of C here. And now let's put some other indices here. Let's imagine that we have another index that's labeling these guys. So let me put some ABC here. So it's actually a tensor, but it's a tensor of dimension 0. And then the only way to satisfy this equation is, for example, if H1 equals H2 is plus and H3 is minus. And then we have, of course, other permutations of that. But in this case, we have 1, 2 cubed divided by 1, 3, 2, 3. Okay, so that's one possible solution. And that's actually very nice because, first of all, we know that 3 spin-1 particles can have a gauge coupling. Now we found something that's dimension 0, so that's consistent with being the gauge coupling. But then we also see that these two gluons have the same, these two spin-1 guys have the same helicity, but if I exchange 1 and 2, the whole thing is anti-symmetric. So this part is anti-symmetric under the exchange of 1 and 2. So that means that it should also be anti-symmetric under the exchange of A and B. So the first thing that that tells you is that 3 photons don't have a self-coupling, which is good because that's what we know. If you repeat the story, you find that it's completely anti-symmetric under all the indices. So that tells you that the minimal number of spin-1 particles that you need to have a self-coupling is 3, and that's also good. That's realized in the standard model. It's the 3 W's, or the W plus, minus, and Z. And beyond that, it's very nice because you see the whole construction of Lie groups from here. So you need something that's totally anti-symmetric. So that's consistent with being the structure constant of Lie groups that we all know and love. And of course, that by itself doesn't tell us that this is really the structure constant of the Lie algebras. But once you go and work out 4-point amplitudes, so once you look at the 4 points, and you require that they have the correct factorization onto 3-point amplitudes, that thing gives you the Jacobi identity. And you see that you really get Lie groups from here. So that's actually one of my favorite examples of seeing a beautiful mathematical structure from the requirement that by asking what are the consistent interactions of spin-1 particles. And I told you that for the massless story, I can do exactly the same for the massive case. The massive case is even more physical because, as we said, this is not physical. and we get this completely amazing result. Anyway, that's kind of an aside to our story, because that's the standard model part. That's the renormalizable part. Okay. So sadly, I'm running way over time. But let me say one more thing, and then we'll finish. Okay. So where was my amplitude? Here. So I was looking at this thing. So now let's try different dimensions for C. So I tried C equals 0. That was the gauge coupling. Now I can try -1. And you can convince yourself that nothing works. And now you can try -2. And you can convince yourself that things do work. And in this case, what we get is C2 ABC times 1, 2, 2, 3, 3, 1. And actually, let me put the scale explicitly here. So let me drop this guy and write it like this. And again, same story. Now let's specify to the interactions of 3 W's. So the only thing that can appear here is epsilon ABC. And again, this thing is completely anti-symmetric under the exchange of any of 1, 2, and 3. And so we see that we got something that's a dimension 6. And actually, if you try other things, you'll see that this is the only thing that you can write down. So the most general amplitude that involves 3 spin-1 particles is this structure, a dimension 6. It has the renormalizable gauge coupling, and it also has the analogous structure with these guys for the negative helicity. And we're going to talk more about that tomorrow. So the first question that we can ask ourselves is this consistent with the Lagrangian counting? And of course, the end result is going to be that, yes, it's consistent, but the Lagrangian counting is more annoying compared to this really, really simple thing that we did. Another thing that I want you to notice is that I started with asking about a coupling of dimension 0 and then switched to dimension 1. And the couplings of different dimensions are associated with different helicity structures. So this is something that, okay, I forgot to say this. In this case, this was the most important thing to say here. What we find is that H1 plus H2 plus H3 equals 3. Okay, so this is the all-class amplitude. And you see that the standard model and EFT have orthogonal helicity structures. So this is something that's quite generic. It's leading order. So it's showing up already in this very simple example. Okay, so I'll stop here, but any questions before that? No questions. Okay, good. Thank you.